So we're going to talk about today is we're going to talk about a couple different things. We're going to talk about atomic radius. We're going to talk about ionization energy. We're also going to talk about, what is it going to be? A photoelectron spectroscopy. So we got three topics that we can discuss today. So the first thing we're going to talk about is we're going to talk about atomic radius. And when we talk about atomic radius, we're really just talking about what is the size of the atoms. And one of the things that's going to happen in your homework assignment tonight is you're going to be given a couple different atoms. And you're going to be asked to, hey, maybe rank them from being smallest to largest, or hey, identify out of the list of atoms here which one happens to be the largest or which one happens to be the smallest. So it's going to be a pretty easy assignment, especially once you understand what's going on here. All right, first of all, when it comes to the relative size of the atom, we have what is called the atomic radius, which is considered to be like the radius of the atom. Generally speaking, when we talk about the atom, what we're looking at is just where is that outermost electron located? Because that's going to kind of dictate the relative size of the atom. So for instance, if I had a hydrogen atom, I could say, hey, you know what? Maybe it's going to look something like this, and we've got like the atomic radius here. Now, of course, if I had some element that's electron was way out here as far as valence electron, I'm going to say, hey, your atom happens to be a lot larger in this case. So when we talk about the actual size of the atom, we're really looking at where is that last electron located, because that's going to end up dictating the relative size, in this case, of the atom. Now, one thing to keep in mind, one of the things that is responsible for really kind of pulling the electrons in with regards to the atom is going to be, of course, the nucleus. That is the thing that is attracted to the electrons and kind of pulling it inwards. And we're going to see that there's going to be some ramifications based upon the number of protons that are actually located in the nucleus. Because if you think about the number of protons, the protons are like magnets. Hey, I got one proton in hydrogen, so that's like one positive magnet sitting there. Over here in helium, which it has two, since it has an atomic number of two, has two protons here. So it's like two magnets, very strong magnets sitting there. So when I look at something like hydrogen, I can say, hey, its valence electron is being pulled in with the force of one proton. But when I go over here to helium, when I look at helium, you're going to notice that, hey, this electron right here is being pulled in with the force of two protons. This electron right here is also experiencing the force of two protons pulling in towards the actual nucleus of the atom. And one thing I know is if I have more protons pulling those electrons in closer, then what's going to happen is the size of the atom is going to actually get smaller here. And I can see that right here, because if you look at the hydrogen versus helium, and I got my atomic radius that's sitting right here. Thank you. It's right there.
Oh my gosh.
It says that, yeah, there we go. It says that when it comes to hydrogen, hydrogen has an atomic radius of 0.37 angstroms, and that's what the A stands for. And you'll look right here, it says, hey, angstrom is 10 to negative 10. I'm not going to test you on knowing the angstrom, but it's typically the unit that we use to represent the atom. Only thing I need you to see is that, hey, when it comes to hydrogen, which has one proton, versus helium that has two protons, you can see clearly the size of the atom is getting smaller. And one of the things it tells you right here, it says, hey, moving across the periodic table, the number of protons are going to increase. And therefore, the nucleus is going to do a better job of pulling those electrons in towards the actual center of the atom in this case. And that's why the generic trend, very basic trend, as I move across, hey, lithium has 3 protons, beryllium has 4, boron 5, 6, 7. The number of protons are increasing, and once again, it's just doing a better job of pulling those valence electrons in this case towards the nucleus, and therefore causing the atom to become smaller. So going across the periodic table, very easy, just getting smaller as we go across. And also, if you look at this picture right here, it illustrates that, hey, as we go across, you can clearly see that the size of the atoms are definitely decreasing. Now, one of the things you'll notice is as we go down the periodic table, the size of the atoms are getting larger. This one, I'm going to show you in a second. If I go back to the previous slide, it's going to explain exactly what's going on here. But this one's really easy to see. If I look at something like hydrogen, so just starting off, in fact, we'll start off with hydrogen. If we look at hydrogen, we can say hydrogen has the electron configuration of 1s1 here. And if I look at something like lithium, I can go, hey, lithium is 1s2, 2s1. And then if I look at something like sodium, I can go here and say 1s2, 2s2, 2p6, 3s1. I'm gonna go one more, potassium. Potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Remember, I told you the size of the atom is based upon where that outermost electron is located. So if I look at hydrogen, I can say, oh, well, it's going to look something like this here. Lithium, well, it's going to be something way out here. Sodium, oh, it's way out here. And if I look at potassium, I can see that the relative size of the atom is getting much larger because the valence electrons are out there in those higher sublevels in this case. So when it comes to the trend of going down the periodic table, we're going to see that as we go down, hey, my valence electron is in the first energy level. Mine is in the second, mine is in the third, fourth, fifth, sixth. That's just getting bigger and bigger and bigger in this case. And that's what you see saying right here. As we go down the periodic table, once again, the electrons are going to be out there in those higher energy levels, and therefore it's going to cause the atomic radius to actually be larger. And we see that trend right here. Here goes hydrogen's size of 0.37 angstroms. But as we go down to lithium, then we got 1.34 angstroms. All right, going to the slide right here. What do we do here? And let's simply say, hey, the atomic radius decreases. I'm going to add this to it because, so as we move across, atomic radius decreases because number of protons I will say are increasing. So simple explanation. The number of protons are increasing, therefore it's doing a better job of pulling, once again, those electrons in towards the nucleus of the atom. And then we said, hey, the atomic radius is going to increase as we go down. And we can go in here and say that, well, that's just because the valence electrons are out in higher energy levels. And once again, if they're out in higher energy levels, then that just simply means they're further away from the nucleus in this case, and once again, causing the atom to be physically larger. So that's pretty easy, not difficult. All right, next thing we're going to talk about is we're going to talk about, you're going to help me out here. We're going to talk about the gentleman who is famous for this equation right here. And the person who's famous for that equation is who? Albert Einstein, exactly. And a lot of times when you go to colleges and universities, you'll see it, the cool kids will kind of have the E equals MC squared on their shirt. And you need to go up to them and say, hey, you know what is C? Someone will be like, I don't know, I have no idea. It's just a cool equation in this case. But in this case, we know exactly what C is, because C is actually going to be what? The speed of light, exactly. And Einstein's equation simply says that if you take mass and move it at the square speed of light, then technically that mass turns into, wait, energy. That's pretty cool if you really think about the ramifications of what this is saying. It's saying that, hey, I'm here. I can be turned into energy if you move me at the square of the speed of light. I think it's pretty fascinating. Wait a second. Where might that be used? I could change into energy. Energy travels at man, that would be pretty fast. The square speed of light. It could be used. I mean, it's not the way they're going to do it, because the problem you have is it's kind of hard to move to the speed of light. It becomes very, very, very difficult, pretty much impossible to do. Even though the universe is expanding faster than the speed of light, but that's something to do differently. But you could think about it as teleportation. Because on here, I turn into energy and then I go someplace else. And then I rematerialize myself, and once again, I come back to being matter in this case. So it's like I'm going from matter, in this case, into energy. But once again, not something we discuss in this class. All right, but let me point one thing out. When I was talking about Albert Einstein, we know that equation. Everybody knows that equation. But what you don't realize is that Albert Einstein did not get his Nobel Prize for the E equals MC squared. He got his Nobel Prize for this thing right here, what is known as the photoelectric effect. But when you talk to most students, they know, hey, E equals MC squared, but they don't know what this photoelectric effect actually is. And we're going to take a look at the photoelectric effect and also some of the implications of this photoelectric effect. First of all, one of the things that Einstein wanted to address is he wanted to address what was going to happen to the electron. Let me explain what I mean by this. He knew that we could take the electron, and so long as we gave it a quantum of energy, it would simply go to the excited state, jump back down. Here goes your photon in this case. One of the things he wanted to address was he wanted to address what would happen if you took the electron beyond the 7th energy level. And keep in mind, when it comes to the periodic table, we said that the periodic table shows us the number of energy levels. Hey, energy level 1, 2, 3, 4, 5, 6, 7. There's 7 energy levels that we know of in this case. So his question was, hey, if I give it enough energy to take the electron beyond the 7th energy level, what's going to happen? Is the electron going to say, nope, sorry, I told you I can only exist on one of these energy levels? Or will the electron actually eject itself out of the actual atom? And this is one of the things that he went in to study. And the way that he kind of studied this is he went back to just using, in this case, electromagnetic radiation. And he used the visible region of electromagnetic radiation. And what he did is he actually shined it on a piece of metal. And what he did is he started off with just very specific red photons. So he went red here. And he gradually started just using energy of photons that happen to be greater and greater energy. Because remember, low energy, higher energy. And what he noticed is that when he actually shot these red photons at the piece of metal, the electron didn't eject out. Maybe the electron promoted up, jumped back down, emitted a photon, but no electrons were being ejected. So he started to go with photons that were over here in the orange region. Still nothing happening. Got into the yellow region. Nope, still nothing happening. It wasn't until he got into the green region that he started to see these electrons starting to actually jump out of the actual atom. And then as he continued on, he was like, wait a second, even in the blue, in the violet, ultraviolet, X-rays, gammas, he was consistently getting electrons coming out. So he simply said, hey, so long as I give the atom this minimal amount of energy, any energy beyond that point, electrons gonna get shot out. It's almost now keep in mind, this is not the same, but it's almost analogous to like the activation energy. Like if I give it enough energy over the hill, if I give it more energy, no matter what, so once I give it that minimum amount of energy, we get a reaction to go. Same thing here. I give it a minimum amount of energy and the electron's gonna end up being ejected out. So if we go back here to the slide here. Oh, not too far here. And once again, what he discovered was the photoelectric effect. And the photoelectric effect simply says that, hey, I need some minimal amount of energy. And so long as you give the electron that minimal amount of energy to take beyond the 7th energy level, then the electron is going to end up escaping out. Now, this minimal amount of energy that we're going to look at is we're going to call it the ionization energy. And we're going to talk a little bit more about the ionization energy in a few minutes. But before I do that, I just want to talk really quickly, about something that we learned in conceptual physics. And that is going to be a piece of metal. Don't write this down. I just want to illustrate to you why the photoelectric effect is really important, how we use it today. When it comes to a piece of metal, if you remember, metals were considered to be good conductors. And in conceptual physics, we told you that metals are good conductors because they have a lot of what? Does anyone remember? They're going to be able to conduct. But remember, space. It wasn't space. It was that they had a whole bunch of just electrons. There's just a whole bunch of electrons that are sitting here. And if you think about it, one of the things that I know is if I can get in here, if I can push this electron, then that's going to cause this electron to shift over, this one to shift, and we get these things to start moving in this case. And if you remember, when we talked about electricity in conceptual physics, we said if we get electrons to move, then that's technically defined as being what? Does anyone remember what that's called? If I think about a river and the water's moving, I say I have what? Current. It's flow, but we call that flow what? Current. So if I get the electrons to start moving, then I got current going on here. So let me kind of point out what's going on here. Where is my remote? Here he goes. Basically what's going to happen in the photoelectric effect is, once again, we can shine visible light here. So I can take white light, just shine it down. Because one of the things that's going to happen with white light is I know that it has the components that I need. It has that green, it has the blue, the violet, the things of high enough energy to get these electrons to kick out. And what's going to happen is when the electrons kick out, they're going to say, wait a second, I'm going to deposit myself right here on this metal. And it's going to say, excuse me, electron, you need to make a little bit of room for me in this case. And this electron is going to say, sure, I will make room. It's going to push that electron, which will push this electron. And as soon as this one pushes down, then another electron deposits itself on the metal. And this thing just keeps on shifting these electrons down. Where could this possibly be used in this case? Using white light. I'm getting these electrons to move. And if I get electrons to move, I got current, I got electricity going on. Where could this be used? They're used in photovoltaic cells. Photovoltaic cells is a nice, fancy technical name for simply saying they are solar panels. So if you think about it, he is actually the father of the solar panel. His responsibility of what he discovered with the photoelectric effect is the reason why we have the solar panel. And one thing to point out, this is a solar panel that I have from a student who was working on a science fair project. She worked on this thing called a algae raceway pond. Really cool thing that she did. But one of the things you'll notice is if you look at the solar panel here, you'll notice how it has these little pieces of metal that run right over top of the actual black piece there. And that metal that's running over top of it is nothing more than, once again, the part that's going to capture those electrons and allow the current to actually be produced. I have these solar panels right here, and this is from Mrs. Greenhall, our nurse's daughter, who did a science fair project. It's a pretty cool project as well. But you'll notice even on these little small little solar panels right here, you'll notice you still have the little itty bitty metal pieces that are going right across the solar panel. And once again, that's just so when the electrons kick off, they can deposit themselves on the actual metal and cause the current to actually produce. And that's the premise behind really how a solar panel is actually working in this case. So just kind of pointing that out to you. Once again, I'm not going to ask you that on a test, but just kind of letting you know why this thing happened to be so important. Hey.
Hi, sorry.
Thank you. All right.
Oh my gosh.
Here we go. So continuing on here. Anything, once again, below the actual threshold, no electrons being ejected. So long as we meet that threshold, and if we provide it with more energy, once again, the electrons get kicked out in this case. And once again, one of the things that we said is that ionization energy is going to be the minimum amount of energy needed for that process. So it's like almost AKA the, once again, activation energy, except for it's different. Minimum amount of energy. So if we look at it, let's just say that the ionization energy happened to be 12 joules of energy. So say it was 12 joules of energy. Then once again, I know that if I hit it with 12 joules, then the electron's going to just kick out in this case. Now, of course, what's going to happen is if I hit it with more energy. So say that, once again, the ionization energy kicked the electron out, happens to be 12 joules, but this time, I come in with a whopping 20 joules of energy. Then basically what's going to end up happening in this case is that 12 joules of the energy is going to go in to dislodge the electron, in this case, from the metal. But then you also have 12 minus 20. Oh, wait a second, where's my calculator here? All right, I believe that's going to be 8, right? Oh man, higher mathematics here. So clearly it's going to be 8 additional joules of energy somewhere. And that additional energy is really going to be found in kinetic energy. Simply meaning that when this thing flies off, it's going to fly off with 8 kilojoules, sorry, 8 joules of additional energy as it flies off. And it's kind of analogous to maybe a baseball player. I can take my baseball bat, I can hit the ball, hit a home run, and it just pops right over the top of the fence. That was like the minimum amount of energy. But if I hit it with even more force, then it's going to go beyond the fence and it's going to continue going off, in this case, with a certain amount of kinetic energy. The same thing applies here. We needed 12 to get the electron out. Every additional amount of energy going into it is just going into making that thing fly off with a certain amount of kinetic energy. That's simple enough. All right, here we go. What we got to talk about just really quickly with regards to ionization energy is we're going to talk about it from the standpoint of trends. What is the trend? And technically the formal definition of ionization energy is the amount of energy required to remove an electron from the ground state of a gaseous atom. And if you think about it, I know that the process happens to be endothermic. Clearly, I mean, if we go back here and look at it, we had to put energy in to get the electron to come out. That's an endothermic process. And that's why you kind of see it like, hey, I got to put energy in, electrons kicking out, and this thing becomes positively charged in this case. But if you look at the ionization energy and the trend of the ionization energy, you'll notice that as I move across the periodic table, so I'm going this way right here, look what's going on with the ionization energy. Hey, boron is like, you need 801 kilojoules. Carbon is like, well, you need a lot more to remove my electron in this case. You need 1,086. Why is it costing more energy to pull the electrons away from the atoms as I move across the periodic table? What could be a logical reason?
Because there's more protons, so there's a stronger force.
That's it. There's more. Who's responsible for holding those electrons in? It's going to be the number of protons in this case. So as you move across the periodic table, you'll see it on the next slide as well. It's going to say, hey, ionization energy increases as we go across because we got more protons pulling those electrons in. And of course, it's going to be harder to kind of physically pull that thing away from the protons. The next one that we got is as we go down the periodic table, so if we go from boron to aluminum, or whether we talk about going from carbon to silicon, you'll notice a basic trend. Hey, ionization energy decreasing. Ionization energy decreasing as well. That was pretty easy also, because if you think about it, if my protons are located somewhere over here, you'll start to notice there's a logical reason why it's easier for me to pluck this electron away than to pluck this one versus this one versus this one. And it's really just due to the fact that, hey, as we go down the periodic table, the atoms are becoming larger and larger and larger, which means the electrons are further from the nucleus, and it's just easier for me to actually separate them. And if you don't remember, or maybe you do remember this thing. Anybody remember this thing? It's like a really cool law.
Oh, the
Coulomb's law. Everything that we're talking about is really related to Coulomb's law. I'm not going to go into Coulomb's law much here. Those who come into AP Chem, that's what we're going to talk about. We're going to talk about, oh, you know what? Hey, clearly, the energy of attraction as the actual distance increases, hey, the energy is going to decrease here. Even when we talk about moving across the periodic table, we're going to say, hey, with more protons, we'll kind of talk about this, then it's going to be a direct relationship with the amount of energy. But it's Coulomb's law. Coulomb's law helps us to explain a lot of things that we're seeing here. So if we look at this slide, going right here, slide simply says that, hey, ionization energy, once again, as we move across the periodic table, ionization energy is going to increase because we got more protons. The more protons we have, the harder it is to strip the electron away from the protons. As we go down the periodic table, then, hey, we said the ionization energy is going to decrease. That's because, once again, these electrons are out there in these higher sublevels, and it just becomes easier for us to pluck those electrons away from the nucleus since it's so far away from the nucleus in this case. And once again, if you look at this picture, you see the trend going on here. Look at that. As I go down the periodic table, well, that was terrible. I didn't get that right. Let's try it again. As we go down, we can clearly see that it's requiring less and less energy going on here. And you'll notice that as we go across, look at that thing right there. We go with lithium, 520, beryllium, 899, boron, 801, carbon, 1,086, nitrogen, 1,402, oxygen, 1,314, fluorine, 1,681, and then neon, 2,081. Clearly, I see the trend. It looks as though, hey, as I move across, it's increasing. I love science. I love it. It just seems to work in this case. Any questions here? Yes.
Why is nitrogen higher than oxygen if it's increasing the more it goes to
Let's just skip that one for now.
Guys,
Yes.
in the orange one, it's going down, but then it's also like one's greater than the last one.
I love science. Why are you going to ruin this for me? I just told you I love science because science works. And now you're going to come here and ruin it with the oxygen and also the boron? I love science though. You know why? Because I got an explanation for why that's going to actually take place. I was hoping somebody was going to actually see this. Now, let me point one thing out to you because this is pretty easy. It's not difficult to understand what's going on here. If you remember, one of the things that I told you is I told you that we had stability with electron configuration. I told you that most stable electron configuration was going to be these noble gases because they have completely filled sublevels. So that's most stable. Second most stable we said was going to be half filled sublevels. And worst case scenario we said would be these partially filled sublevels. So basically what's going to happen when we look at this boron family right here. The boron family is going to look something like this right here. So if I look at boron, it's going to be 1s2, 2s2, 2p1. Boron is like, man, I am so close to having great stability, completely filled sublevel. All I got to do is just give that one electron away. You know what? I'm not putting up a fight for it. Take it. Go ahead. Remove it. Same thing with aluminum. Look at aluminum right here. 1s2, 2s2, 2p6, 3s2, 3p1. It's one electron shy of having completely filled sublevels. So what aluminum's going to go in here and do is it's going to say, hey, you know what? Take it. I'm not putting up a fight here. So one of the things you're going to see right here in the notes is it says, hey, when it comes to the boron family, and it is an exception. And once again, basically what it's trying to do is it's just trying to, once again, give away that electron so it can get to this great stability of having completely filled sublevels. Yes.
Is it the same thing with the oxygen family, but they're trying to get to half-filled?
That's exactly it. When we look at the oxygen family, you're going to see that right here. The oxygen family is like, hey, and this is going to be true for the whole entire oxygen family. They're always going to have their valence electrons being something like this right here. Just like right here. And it's like, man, I am so close to not being the stablest, but the second most stable electron. I don't like this. This is partially filled. So what it's going to do is, once again, it's going to simply not put up a fight for the electron, and it's going to say, I'm going down to stability in this case. So when it comes to these two families, the only thing I need you to know is, once again, kind of the rationale for what's going on here. Because I can easily put this as a multiple choice question. I can say, hey, the oxygen family has a tendency of actually having a lower ionization energy than what's expected. A, because of this, B, because of that. Just kind of know what's going on here. Yes, Lou? Absolutely. All right, here we go. We are just about finished. All we gotta do is cover one more topic, and then we're gonna be pretty good here. So what we're gonna talk about now is we're gonna talk about the photoelectron spectroscopy. Wow, that is a mouthful to say. Let's see what's going on with this concept. When it comes to photoelectron spectroscopy, basically what we're going to do here is we're going to look at removing every one of the electrons out of a given atom. And the way that we're going to do this is typically they like to use X-rays or ultraviolet rays. Just get in there and just, once again, eject every single electron. Keep in mind, generally when you start ejecting electrons, just to point this out, like if I was to start going from low energy to high energy and I wanted to eject electrons out of maybe, say, potassium, the first electrons that are going to go are going to be these electrons out here because they're furthest from the protons. Then these electrons will be the next one that would go. Then these electrons and these, because once again, as you get closer and closer to where the magnet is, the protons, then of course it's going to be harder and harder to pull those electrons away. And you're going to kind of see that play out here. So all we're going to look at is removing every one of those electrons. So let me tell you right here, electrons that are closer to the nucleus are harder to remove, and that's because they're closer to that attraction thing, which is going to be the protons. The valence electrons, which are furthest from the nucleus, are going to be the easiest to remove because, once again, they're furthest away in this case. And we look at this thing known as the photoelectron spectrometer, which is the instrument, this thing right here. that's responsible for actually producing this thing, once again, it's going to end up producing this graph. And the only thing we got to do is learn how to interpret the graph. And normally what I'll tell you is that when you first see it, you're gonna be like, oh, I don't necessarily care for this. But then you're gonna be like, oh, I can't wait till this is on the test, because this is just like easy points in this case. So let me kind of explain what's gonna go on here. And then I'll just show you some examples. As we walk through the examples, it's gonna start to resonate and kind of click with you. Basically what we're gonna have the y-axis. On the y-axis, it's gonna give us the relative number of electrons. I'm gonna show you exactly what I mean by that. We'll also have the x-axis, and on the x-axis, it's going to go from low energy, typically up to higher energy. And basically what's going to end up happening is we're going to end up getting some actual charts that look like the following up here. And one of the things that you're going to be responsible for doing is kind of going and looking at these charts and saying, hey, you know what? That happens to be maybe carbon or nitrogen based upon this actual spectrum. And what we're going to do is we're going to start off by just going right through a couple of elements that we already know. And then I'm going to give you some elements that we don't know. We're going to see if we can actually identify them. So for this one, this is hydrogen. Hydrogen has 1 electron. And what you'll notice is right here, it says number of electrons. Right there, it goes up to the height of 1. Okay, well, 1 electron got ejected out of this thing in this case. If I look at helium, you'll notice that, hey, for helium, it has a peak here, but it represents 2 electrons. Also, just point one thing out. Notice how it shifts between hydrogen and helium. Oh man, it costs more energy to pull the electrons out of helium than hydrogen. I already said that because the number of protons are increasing, so of course it's going to cost more energy. But once again, just point it out to you. The next thing that we have here is we got lithium. So if we look at it, what I know here is that once again, with lithium's electron configuration being the following, lithium, 1s2, 2s1. I already told you that the electrons that are going to be the easiest to pull out is going to require the least amount of energy. The ones that are going to take the greatest amount of energy are going to be the electrons that are closest to it. And one of the things that you'll notice is that, hey, I got 2 electrons right here. That means this represents 1s2. As I go down, I'm going to say, oh, that's just 1 electron right there. So that's going to be 2s1. So 1s2, 2s1. I'm going to start identifying each and every one of these peaks in this case. If we look at the next one, beryllium. Beryllium has an electron configuration in this case of 1s2 and 2s2. And what you'll notice is if I had to write the electron configuration and say I didn't know this was beryllium, then I would go in here and I'd say, okay, you know what? I always start off with the 1s, so this would have to be 1s2. Okay. The next sublevel I gotta go to is gonna be the 2s. And this is 2s, that's 1, 2. Okay, 2s2. I identified it. It has to be beryllium in this case. Show you another example. Say I gave you phosphorus in this case. And let's just say I didn't even know this was phosphorus. I don't know. Don't even know it's phosphorus. Then what I'm gonna do is I'm gonna go here and say, okay, well, hey, those require the most amount of energy. So I'm gonna go in here and say, you must be 1s and 1, 2. Okay, 2. Next, I know 2s comes next, so 2s, 1, 2, 2s2. After the 2s based upon the periodic table, I go to my 2p sublevel. And that says 2p all the way up to 6. Okay, 2p6. On the periodic table, I know what comes next is 3s, that's 1, 2, 3s2. And then I go to my 3p, I'm gonna go 1, 2, 3, 3p3. Hey, and if I go across the periodic table, 3p3, oh, that's phosphorus. And then once again, same thing, we had something like calcium here. Once again, I would go through and I would kind of look at it and simply say, okay, well, it's 1s2, 2s2, 2p6, 3s2, 3p6, and after the 3p comes the 4s, and that's 1, 2, so 4s2. All right, what we're gonna do now is we're gonna identify a couple of elements. And then after that, I'm gonna explain what your homework is gonna consist of. So here we go. Starts you off with a hard one. Man, it's a difficult one right there. If you look at this one, what element is it gonna be? Helium, exactly. Because that's just 1s2, and 1s2 matches up in this case with helium. Got it. For the next one, let's see what we got right here. For this one, got it. This one's gonna end up being what? Phosphorus. Because once again, this would be 1s2, 2s2, 2p6, 3s2, 3p, 3 in this case. Here we go. Let me explain what you're going to have as far as your homework for tonight. On Veracross, get here, here. Website. Oh, right here. So on Veracross, you're going to notice that there is a additional worksheet that's in here because we already finished the other worksheet. It's called Atomic Radius, Ionization Energy, and the Photoelectron Spectroscopy Worksheet 2025. So basically what you're going to do is you have it says 28 problems. There's only 26. I was trying to add some more problems, but when I was adding the problem, I recognized that I added a duplicate problem. So you're only doing 1 through 26. I'll tell you on Veracross as well. So basically what's going to end up happening for this homework assignment is you're going to go in, you're going to answer all the questions. So it's just multiple choice, all the questions, multiple choice. After completing the assignment, you're going to go into Shelby. You're not going to dump this worksheet in Shelby, but instead there's going to be a little Socratic kind of, it's going to say Socratic quiz. Just going to put your answers in there. So what we're going to do is just do a couple of problems together. So for instance, if we look at number 1, it says, hey, which element has the largest atomic radius? And one of the things you're going to notice here is we got aluminum, silicon, phosphorus, sulfur, and chlorine. So it looks like we're just doing this, moving right across the periodic table. Which one's going to be the largest in this case? Aluminum. So there we go. Because I know that once again, the size decreases as I move across because we got more protons. So that was one with the atomic radius. Let's look at one with the ionization energy here. How about this one right here? Number 11. I gave you the halogen family, and the question is, hey, which of the following has the lowest first ionization energy? So the lowest amount of energy to strip away its electron is going to end up being who? A, B, C, D, or E? E. Because once again, we know that as you go down the periodic table, those valence electrons are further and further and further away from the nucleus. Easier and easier to strip those things away in this case. So definitely going to be E. The next and last one that we'll take a look at is going to be this one right here, 23. Try 23 and 24. I just want to make sure everybody's comfortable with this before I give you the rest of the problems. So 23, they want you to just identify, in this case, the element. And then try number 24, and then we'll go over the answers and see how you made out with this one. All right, everybody finished? Yep. All right, so first of all, we got to identify what this element is going to be. The element of this one is going to end up being what? Neon, right? And be careful here, because if this one, you'll notice that, hey, that's not one electron, that's actually two. That's 1s2, 2s2, 2, 4, 6, so therefore it has to be neon in this case. For the next problem, they're simply going in and saying, hey, if peak 1 and peak 2 are S sublevels, what is going to be peak number 3? And peak number 3 is going to fall into being what type of sublevel? What is it? B, exactly. And now one of the things to point out, this problems I just gave you are actually old AP chemistry problems. That's the complexity that you would see for those who go into AP Chem. But this is easy. I mean, once you start to just appreciate it for what it's worth. Will there be problems like this on a test? Absolutely. Do I expect for everybody to ace it? I hope you will in this case. All right, with that said, we got 3 minutes